And I'm very happy to be here. So I'm originally from Prague, but I have been living for several couple of years, like outside of my hometown, Prague. And it's always good to get here and see how the crypto scene is growing. So this is the second year actually I'm attending ETH Prague, and it's good to be here also as a speaker this year. Yep, paráda. And today I will be presenting about my insights into research that is focusing on trusted execution environments. So for those of you who have been here since the early afternoon, definitely I think we have heard in most of the talks aspects of TEEs, and in my talk I will be diving a bit more into the details of actually what is a TEE, what are the different manufacturers out there, and actually maybe you can think of some use cases for TEE during the development of your solutions. And in the second half of the talk, or rather coming to the end of the talk, I will also touch on an aspect of a framework that we have developed at the chair that is aimed to be used for actually assessing the capabilities of the different trusted execution environment technologies, but not only limited to that, but providing a general scope. The work is part of a larger team of people, my colleagues at the chair that I have been working with for the several couple of years, not only on this framework, but other aspects as well. And as a chair of network architectures and services, we are in general looking into the aspects of distributed systems and looking into the network security protocols and other parts. So if you're interested, feel free to scan the QR code and find out what other research we are actually doing. So without further ado, let's get started. So I believe some of you are already familiar with the general concept of what TEEs can be used for. This is not, of course, covering all of the aspects and use cases you can think about, but the general idea is that, of course, in order to scale the performance of the chains, you can do certain off-chain computation in order to later on just provide a certain proof or commitment on the chain that can be later on used to basically provide additional computation off-chain. Of course, there is other solution that is much more popular, that are ZK rollups, but in some way, TEEs can provide a similar type of use cases. Of course, the general part of the TEEs is focusing on the compute and proving, where you later on can store the computation on the chain, where people in a smart contract can later on verify it and get information about that. But of course, there are additional use cases you can think about. So it can be, of course, used also for privacy when it comes to encrypted mempool transactions, Sybil resistance due to the aspects of the attestations, and other parts as well. So, of course, depending with whom you speak, there will be a bit of controversy between the people that support these or not. From my perspective, I don't generally see it like a silver bullet that should be used for all types of solutions, but you can think of it like a defense in-depth mechanism where maybe using TEEs can provide some additional security guarantees, and definitely I think they are worthwhile technology to have a look at because they are quite mature and they can be already used in nowadays systems. So providing a bit of context, what is actually a trusted execution environment? So you can think of it like an isolated region in a CPU. So for that, it actually means that the hardware manufacturer has to provide this information and this aspects inside of the CPU. So when you are ordering a CPU, you have to actually verify that the CPU is supporting the corresponding trusted execution environment technology. And in general, it aims to promise to be secure location for code and data on the CPU itself. And the main attributes of trusted execution environments is that it offers confidentiality, meaning that no one else, either the other users in the system, can read the data, and it also offers integrity, so that way in case you're interacting with the TE, you can ensure that the data that you have interacted with were not tampered with and are actually functioning. And in order to make it usable, you can also generate attestation reports that you are later on sharing with anyone else, and they can verify that actually, okay, this type of computation has happened inside of the trusted execution environment, and they can actually trust that the computation and the outcome of it is correct. Diving a bit more into the attestation, so again, this is actually an aspect that is varying quite significantly among the different manufacturers, but the idea is that it allows you to measure and attestating the state of the system. So for example, it can provide you information in the policy of the corresponding attestation is what operating system are you using, what is the corresponding hash of your code that is running inside of the TE, and many other information. And this information, in order to be trusted, actually has to be provided in a form of root of trust. So that way, even in the manufacturer of the CPU is basically helping you to issue a certificate to your corresponding TE. So that way, you can have the root of trust from the manufacturer to the user of the TE until basically anyone, third party, can verify that this computation has happened inside of your TE. And of course, for that, you are using typical public key cryptography, that you are just signing the report inside of the TE itself. There can be added also depending again on the type of manufacturer. You can also have some granular control, and you can be adding additional custom data to this attestation report. But again, for that we don't have time to dive into details, but in general we can see that this is something that is a welcomed feature to have when it comes to the usage of TEs. There are two main categories of trusted execution environments, process-based and VM-based solutions. So on the right side, we can see the process-based solution. So this is the implementation inside of the cloud. But of course, you can also think of it when you have your bare metal solution, where you will just basically skip the hypervisor. And that means that your application has to be specifically written in such a way that it will be interacting with the trusted execution environment. And you basically have a hook to the corresponding trusted execution environment secure enclave on the system. And parts of your code will be running inside of this enclave, and you will specify using this interaction in the SDK what types of code actually should be running inside of the enclave itself. And for those operations that will be running inside of the enclave, you will ensure the additional security properties. On the other side, we have the virtual machine-based solutions. In this case, you actually are running whole your application inside of the TE, where we are not only talking about full-fledged virtual machines, but it can be also containers. So for example, I guess many of you have heard about Docker containers. So those cannot be easily run inside of a TE. But there are other solutions, for example, like runc containers or kata containers that basically allows to be run inside of a TE, either individually or on top of a virtual machine that is fully running inside of the TE itself. So, and later on when the corresponding application wants to interact with the TE, it's basically leveraging the secure instructions that are provided and are a part of the instruction set of the corresponding CPUs. There are several manufacturers, so basically most of the modern CPUs are either coming from Intel or AMD, and for those we can see the colors in green correspond to the process-based solution. So we have Intel SGX, that I would say is quite established technology, has been around for quite some time. That is process-based solution. We have Intel TDX, a new solution coming from Intel, that is a VM-based solution. From AMD, we have different versions over the years of AMD CVSNP that is adding additional features for confidentiality and integrity. Then we also have RISC-V Keystone project, but there is also additional parts that can be added to that. And from ARM, we have the Trust Zone, that is like very established technology, pretty much used in every modern smartphone. That is also a process-based solution, but also we see a successor of ARM Trust Zone that is called CCA, and actually for that one we will see a shift towards the VM-based approach as well. So the reason I briefly already touched on that, why the VM-based solutions are maybe more attractive for the new technologies, especially the aspect that you don't have to do too significant modifications for your particular code. So you can just take your application, run it inside of your container, and you will basically be adding these additional security features on top. And of course, you have to later on interact with the additional tooling to be able to generate the attestations to convince others that actually your code has run properly inside of the TE and is providing the sufficient features. So still you have to, of course, consider what are the features you are interested in, but the usability should be much better when it comes to that. Of course, when looking into the other aspects, I already touched upon that, memory confidentiality, memory integrity, CPU state protection, and molestation, all of these are provided by the modern technologies that we can see here. For example, when talking about ARM Trust Zone doesn't provide the remote attestation capability, so that way you cannot easily convince others that your code and your toolchain was actually running inside of the ARM Trust Zone itself. And of course, the main difference is the aspect of the fine-grained control. So of course, with using the VM-based approach, you are losing this fine-grained granular control because you are running whole your code itself, whereas for the Intel SGX, you are actually running only certain parts that you can assess and ensure that they will be running inside of the trusted execution environment. Also looking into the accessibility of it, of course, there are already CPUs you can buy. You can just buy your own bare metal and deploy it very easily locally. I mean, easily. It's kind of plug and play depending on the solutions you want to use. We have quite some experience with running our own bare metal solutions for majority of the TEs that you can see on the slides. But also for accessibility reasons, you can also consider having a look at cloud providers. So GCP, Google Cloud Platform, Azure, AWS are basically already providing most of these TE options. Intel TDX is rather new, so for that one we can especially only have access in a public review. So this is something that actually we have an access to and are looking into the usage of Google Cloud Platform together with Intel TDX. And continuing with the second part of the talk, it's, as we can see, there are different trusted execution environments. All of them are providing slightly different guarantees when it comes to security, usability, and other parts. And for that, we are looking into the ways on actually how to be able to assess in a structured fashion, firstly, the capabilities of the TEs, and especially looking into that in the context of distributed systems, blockchains, cryptographic protocols, and other parts, and be able to collect insights in a reproducible fashion, be able to compare how the different architectures, either of TEs or the applications running inside of a TE, can differ, and identify a common ground that can basically later on help to collect the insights and minimize the external noise of such deployments. So I believe most of you are in some way familiar with the stack on the right side. So of course, mainly on the application layer, we are interested in the blockchain stack, right? That where basically we have our data layer, network layer, consensus layer, execution layer, and others. But of course, the blockchains are not coming out of a thin air, right? They are building on top of internet, and of course, the corresponding physical layer and others are part of the whole stack that the corresponding clients that are running and participating in blockchain have to be considered of. And the part that we are mainly interested in is how does, when we integrate, for example, TEs, especially the VM-based solutions, affect the upper layer solutions in such a way. So our framework is basically allowing to deploy the aspects in a cloud deployments, but also in a local deployments. Meaning that, for example, you can take Ethereum client and deploy it in cloud or local deployment inside of a TE and see actually how does it affect the performance, but also how can you actually interact with it and be able to create the corresponding attestations. And of course, in order to be able to collect valuable insights, we have to do some theoretical assessments, like be actually diving into the security guarantees, into the white papers and others of the corresponding system to see how it behaves, see if actually if it's matching to the code itself, and later on do some testing. When it comes to the evaluation metrics, there is of course plethora of metrics you can play around with, also plethora of parameters you can modify, so we don't really have time to dive into that in such a level of detail, but in general, what we are aiming for is to have a granular control over as many parameters and be able to collect information about as many metrics as possible. When it comes to actually deploying such experiments, we are calling the framework Methoda, and we have an orchestration from a management host that basically where we define the corresponding inputs, meaning, okay, we want to run, I don't know, 80 different Ethereum client nodes in our environment. That will be distributed over several physical nodes. Some of them can be running inside of a TE, some of them will be running just as a typical virtual machines or other parts. Then later on, we have the system under the test where we are collecting the insights about the system performance and properties. And later on, we are collecting all of the information from the corresponding run, and we are able to collect later on the insights about the system properties itself. Since we were talking especially about TEs, here are some preliminary experiments where we can see two types of experiments for the CPU compute-bound triad metrics and CPU memory-bound, for which we use the computation of matrix dimensions, where you can see on the x-axis the corresponding dataset size for the triad on the left, and on the right side the matrix dimensions for the memory-bound experiments. And then we can see the execution duration in seconds on the y-axis for the triad on the left, and number of floating point operations on the matrix dimensions. And we have been comparing 4 different technologies inside of our local deployment, where we have a baseline, which is basically no virtualization, no trusted execution environment itself. It's just basically the bare metal performance. We have then a Docker container, kata container, and a kata container inside with the trusted execution environment. And basically, their experiments are showcasing that the modern TE's performance implications are rather comparable actually to running a bare metal performances itself, which actually is showcasing quite nicely the majority of the technology, and it can be quite easily used for certain CPU-heavy tasks and does not provide as much of an overhead when used. So in today's talk, we covered the aspects on how these can be used for scalability, and we covered also the framework that we are using for such solutions. And overall, we consider that this could be applicable to many solutions out there, either for scalability, other aspects of private compute or general private compute on permissionless blockchains, big topic, decentralized physical infrastructures and others. What we have also heard in the previous talk that we didn't manage to cover in the talk this time at all is we actually start to see trusted execution environments on GPUs. So that way, when you are, for example, running certain training of the data, you can easily run it inside of a GPU itself. And overall, what we can imagine, it will be a good stepping stone to achieve the holistic view on how the TEs can be used together with other types of blockchain application, and we'll be able to see how it can interact with the individual layers. So with that, I'm coming to the end. If you're interested, feel free to check our preprint publication, and I will be happy to connect and take any of your questions. Thank you very much.